Alright, here today, the next part of the differential equations, we're working on what's called separation of variables. So here's a general kind of form, if you like. So your differential equation, your dy dx, your differential bit, it could have an aspect in terms of x and an aspect in terms of y. So your x and your y obviously are your variables, but here dy dx, and then we've got an expression which has got something to do with x and something to do with y, separate things that are multiplied together, needs to be multiplied together. So what we can do here is we can, this is where we call the separation of the variables, we can multiply both sides by dx, and we can divide both sides by g of y. And when we do that, then what we would end up with is 1 on g of y dy. Now, of course, that looks like an integral, so we need an integral sign. And I mean, what I've said there is really simplifies what the proper mathematics is, but it's effectively anyway. And the other, this side over here, of course, is fx dx. All right, so that's what we talk, what we would say separation of variables. Here we've got our variables x's and y's mix, and then we separate and put them on separate sides. So of course now if we've got a function in terms of y, we can anti-differentiate with respect to y, and on the right here I've got my function in terms of x, which I can differentiate with respect to x. Alright, so if we have a look at first an example, so you'll see that, let me just change my colour. Alright, so this here, that's our function of x, that's in terms of x, whereas this one here, that's our function in terms of y. Alright, so what we then need to do is we then need to say, okay, well, the dy is here, so we'll leave the dy on the left, and we'll bring the y, the 1 plus y squared over, so 1 on 1 plus y squared, integral of, equaling, and so here's our integral of our x, e to the 2x, with respect to x. Alright, so that's where we've rearranged that. Alright, so if you've got your formula sheet that VCAR gives you handy, and you look in here, this one looks like, and in fact is, the inverse circular function tan. Alright, so that one's tan minus 1 of y. And again, remember, plus some constant. And over here, it's an e to the x, so remember e to the 2x is still e to the 2x. But of course, we've got the constant we need to bring into, and when we're anti-differentiating, there's nothing there already, so we need to have a half. All right, and then plus some constant as well. Now, there's no guarantee that that one is the same as that one, so call it different. However, having said that, given that they're both numbers, all right, slash constants, if we what I can actually do is I can put them both together, and I can just use one constant instead of having to work with two to simplify things. Because remember, they're both numbers anyway. Put them together, put two numbers together. What do you get? You get another number. So what I'm going to do is I'm going to say, all right, well, if we combine them, and so I'm going to combine them, I'm just going to call it E, is what I'm going to call it. Then tan minus 1 of y equals a half e to the 2x plus e, whatever e is. All right, and the reason why I put it over here was we want our final answer, of course, because our dependent variable is y, and we know that because up here, right, dy dx, so that's the one on top there is our dependent variable, the one on the bottom is our independent variable. So we always want then y equals, where possible, for our answer. So I'll put the constant over here on this side. If I had to put it over here, I'd have to move it anyway. All right, so that's a bit of information about that. Now we want y equals, so we've got to undo tan minus 1. Of course, just take tan of both sides to do that. And so that's the tan of a half e to the 2x plus e, whatever e is. And of course you would need some information to find out what e is if we needed to. All right, so there's our separation of variables, as it's called. So basically it means get everything involving x on one side, everything involving y on the other side, and then going from there. All right, another example. This example's in the textbook, and it's in the textbook, the Cambridge textbook, on page 397. Right, so Cambridge, page 397. And it says here, a tank contains 30 litres of solution of chemical in water. The concentration of the chemical is reduced by running pure water into the tank at the rate of 1 litre per minute, and allowing the solution to run out of the tank at 2 litres per minute. The tank contains X litres of the chemical time t minutes after dilution starts. Show that dx dt is that, and a general solution, and then a fraction. All right, let us have a look. So first of all, we've got this we've got this tank. There's our tank. There it is. So the question is, let's worry about the concentration, or how much stuff of this chemical is in there, a little bit later. But what we will do is we'll have a look. How does the volume in the tank, how does that change? So our volume is, so initially we got 30. Runs pure water into it at the rate of 1 litre per minute. So, and if I'm using T for minutes, so 30 plus 1 litre for every minute. And then it runs out, so we're going in at 1 litre per minute, and we're going out at 2 litres per minute. So 2t. So we've got 30 plus t minus 2t. So overall that's 30 minus t. So we know how much water we've got in there at any particular time. All right, so what else do we know? Well, this x is the amount of chemical in the tank. All right, so the fraction of the chemical in the tank then. Ugh. Let's get rid of that. Let's rewrite that. Fraction of chemical in the tank. All right, up here it says that the tank contains X litres of the chemical in time t. So the fraction of it then would be how much you've got, X litres over, so you've got X litres of chemical, but we've also got some water in there as well. And so what's actual volume? Total volume. So the fraction of the chemical is a fraction of the total volume. So how much chemical over the total volume, which we figured out up here to be 30 minus T. All right, so then where are we going? So the rate of flow of the chemical is what we are then after. All right, so same dx dt, so the rate of the flow of the chemical, and so the rate of flow all right, is the chemical, so focusing on the chemical. So now we'll have a look. So right, we had some water in here, we had some chemical in here, we've got some pure water coming in, it's mixing with that, and then we've got this stuff coming out. And the stuff that coming out's got our chemical in it, plus some water. So what's coming out has this fraction here. All right, so whatever's coming out, so 1 litre comes out, then what we have in that 1 litre is this much of the chemical, because that's the fraction of the chemical that's in there altogether. All right, now here it's coming out at 2 litres. So what we're talking about, because it's coming out of the tank, then it's negative, isn't it? So it's negative because it's reducing, the amount of chemical in the tank is reducing because it's coming out. And how much is it reducing? Well, it's reducing at 2 litres per minute, and each litre has a fraction of x over 30 minus t of the chemical in it. So the rate of flow of chemical, well, rate, of course, rate. So that's to do with time. So we're doing d something, d to time. And the chemical, well, that's x, isn't it? So this, what we're figuring out here, the rate of flow of the chemical, is dx dt. And so it's negative 2x over, excuse me, 30 minus t, which is what we were after in the first place, or what we were asked to show, I should say, not what we were after. We were asked to show that. All right, so what do we know? We know the volume of the tank in any time. We've got a certain amount of chemical in that tank, and so the fraction of chemical out of the total volume is how much chemical we've got over the volume, and the rate of flow of the chemical, which is what dx dt is, because it's coming out, the amount of chemical in there is decreasing, so negative, it's coming out at 2 litres per minute, so negative 2 times the fraction of that 2 litres that has the chemical. So there it is. All right, part B. And I'll just point out, whenever these questions, if you get one on the exam that says show, and if you get stuck in part A and you're not sure how to show, you can still do part B. All right, because they've given you the differential equation you need to solve part B in part A. So be careful with those kind of things on the exam when it says show and then you've got a subsequent question. If you get stuck on the first part, you can still do the second part. All right, so part B. So now we've got dx dt is equal to negative 2x on 30 minus t. All right, so now we need to separate our variables. So we've got x and we've got t, and over here we've got a bit with x in it, we've got a bit with t in it. So we need to separate them. All right, so we need something to do with dx, and we need something to do with dt when we separate them. So that means I've got to bring this 2x over there, and so that's 1 on negative 2x. And the dt, well, that's come across if you like, and we've now got 1 on 30 minus t. And so now we're going to solve that. All right, so let's have a look. So I can take negative half out here as a constant, a factor, and we've got 1 on x dx. On this side over here, it's not a lot I can do there. I'm going to probably leave that as it is, because there's not much I can go about doing there with that. And so that stays where it is. So it's going to be 1 on log. Oh, sorry, not 1 on log, 1 on 30 minus t. So there's going to be a log. I'm getting ahead of myself. So this log's involved in both sides here by the looks of it. All right, left-hand side, negative a half, log to the base e of x, equaling log to the base e of 30 minus t. Now, here we're going to be careful with this one here, because when we're coming here anti-differentiating, just remember if we were going the other way differentiating, we'd use the chain rule. So you get the 1 over from the log, but then remember you've got to do the derivative of this. Now the derivative of 30 minus t is minus 1, so there's a negative that's got to go in with this as well. So given there's none up here, there it is there. And I'm going to go plus c, and I'm only putting a constant on one side for the reason that I explained in the previous example. All right, so what do we got there now? Now we've got a bunch of stuff. We've got a bunch of stuff that we can then rearrange. So if I go then the log to the base e of x, so 5 times both sides by minus 2, then I would get 2 log to the base e of 30 minus t. When I do that together, that's minus 2c, which is just a constant anyway. So it's just a constant. Try and keep things simple. Plus a d. You can even not even worry about going and changing the letters there of your constant if you want, but plus a d. All right, so what do we got to look? Is that it? Is that what I'm after? Let's go here. Find the general solution of this differential equation. All right. Yep. Let's have a look. So what else can we do there? All right. So if we let the amount, if we let now when I'm getting myself backwards. So when time equals, when, can't spell now, when time equals 0, let the amount that we've got equal A0, the amount at the start. Okay, so if we let the amount at the start equal A0, we can now put some stuff in here. And so when we do that, we go log to the base E. And so this is going to help us later when we get to part C. But so if we just say, all right, the amount at the start is A0, that's how much we started with. So of A0 would be equal to 2 log to the base E, I forgot the E here, of 30 minus 0 plus D. All right. Now, what I haven't done with this 2 here, of course, can come up there. And so I've got log to the base E of A0, the amount at the start, is log to the base E of 30 squared plus D. 30 squared, of course, is 900. But what I can do to find out D is I can move this across. And so I've got log to the base E of the amount we started with minus log to the base E of 900 is equal to D. And of course, as we know, when we go log to the base E of the amount we started with over 900. And so that is our constant. And so now we can whack that back in. Where are we there? Plus D. There it is. And I can put that squared up there at the same time. So I've now got that x equals log to the base E of x, I should say, of x equals log to the base E of 30 minus t, and I'll put that squared up the top. All right, yep, that's that there, so I'll put that there. Yeah, plus the d, and the d is log to the base E, the amount we started with over 900. Now, of course, when we're adding, we can combine our logs together, and when we do that, when we combine our logs together, we multiply these two things. I'll put the constant at the front, and there, so then we've got that, so we've got log to the base E of x is that. So our general solution then, to get rid of the log base e's, we can do e to the power of on both sides, and so x would be equal to a0 over 900 times 30 minus t all squared. So that's how much we have got in our tank at any given time. So let's just shoot back up here, find the general solution of this differential equation. So how much we've got of our chemical at any time, and there it is, based on the amount we started with. So it's going to vary depending on how much of this chemical we started with. All right. Then where we go up here, part C says find the fraction of the original chemical still in the tank after 20 minutes. All right. So remember, A0 is the original amount of the chemical that is in there, and so we'll get to that a little bit later. So but time equals 20 minutes. And now I'm going to just shoot back up the top there and check again to make sure that's what time's measured in. Whoops, too far. Per minute, time in minutes. Okay, so I don't need to do anything with that. So how much have we got of our chemical after 20 minutes? Squared, and so that would be a naught, how much we started with, 900 there, times 100 here, and 100 goes into 909 times, so it's A0 over 9, and that of course can be written as 1/9 times A0. And remember, A0 is the amount we started with, and the question's asking us what fraction remains. And so if we started with A0 after 20 minutes, the amount that we've got, X, is 1/9 of that. And so how much of the original remains? 1/9 of the original. All right, so there we go. So there's our separation of variables, as it's called. Remember, so there's a mix of variables, and then we separate them to either side. So we have each variable just on one side of the equation, and then we can do our integration, anti-differentiation around that. All right, so if you need assistance, make sure you get some. And as always, have fun.